Lesson 251, Analyzing Exponential Functions. This zombie hamster here is going to be going on quite a journey this lesson. Okay, so our objectives for this lesson is how do I interpret exponential functions in the form f of t equals a times 1 plus r to the t power. And we're going to be using this for all our examples here, and we'll go over what each one of those variables symbolizes on the next slide. Second objective, what is growth and decay and how do you determine it? And 3, we're going to apply these in real life. Okay, so that formula that we were talking about, our exponential model. So we have f of t equals a times 1 plus r to the t power. Okay, so this f of t is what we're going to be solving for. Right, so this is if it says in a certain amount of years, what would the population be? This is going to be what the answer is. Now this a here, it's an important piece of information. A is our initial amount or our starting amount, however you want to look at this. Okay. Our rate is embedded inside the parentheses. Okay, so again, that if you guys understand that, that'll take away from a lot of confusion. So even though this is 1 plus r here, the rate is within the parenthesis and we can solve for it. And lastly, our variable t, that is our time in years. Okay, and you always want your variable to just be t. You don't want it to be a number and t. You don't want it to have a coefficient. So you never want this to be 3t. You only want t. Okay, now prereq skills. This goes back to the very first lesson that we did, the exponential powers. And this is the power to power property. Okay, so the power to power property, so even review before we do these two. The power to power property was when we had 2 raised to a power raised to another power, let's say 2. And when we have an exponent raised to an exponent, we multiply those. So here we would have 2 times 2, right? Because that's this exponent times this exponent. And that would give us 2 to the 4th power, or 2 times 2 times 2 times 2, which is 16. Okay. For these prereq skills, we're actually going to be undoing this. So we're starting with it from right here, and we're going back this way. Okay. So let's do the first example. We have 12 to the 3t power. Right? So we want to make it look like this here. So what we're going to do is we're going to split that the number 3 and the variable, the t. So what we're going to do, we're going to have our 12 raised to the 3rd power raised to the t power. Right? Because we simplify that out, we multiply the 3 and the t, and that's what's being done there. So we just undid it. Now, we always check to see if you can simplify, and 12 to the 3rd power gives us 1728. And don't forget to raise that to the t power. And parentheses are not necessary there just because you only have one. You have 1728 and a t. Okay, next one. Same steps. We don't have a variable by itself for the exponent, so we want to split these. So we're going to have 4 to the negative 2 power raised to the t power. So exponent raised to an exponent. Now we have that negative exponent property rule that says that when we have a negative exponent, you got to reciprocate your fraction. So 4 to the 2nd power is going to come to the bottom. 1's going to go up on top. Right? Since we took it and we moved it to the bottom, it becomes positive. And this is all raised to the t power. And one last step for simplifying, 4 squared can be simplified. That's just 4 times 4, which is 16. So this is 1 to the 16th power raised to the t power. And now we have t by itself. We're satisfied with our answer there. All right, converting percents to decimals. So percents to decimals will be moving to the left 2 times, right? And a lot of people remember it because there's 2 zeros on the percent sign right there. So you move 1, 2. And any space that you have a little dip in, you fill in a 0. So percents to decimal, this will be 0.036. Now for the next one, converting decimals to percents, you move to the right 2 times. So 1, 2. You get 2.3%. Okay, and we're going to be doing that quite a bit for this lesson here. It's going to ask for the rate and then percent rate. So make sure you guys kind of get that down. Okay, first example. Find the percent rate of change for f of t for each of unit t. State whether the function shows exponential growth or exponential decay. Okay, so let's find the percent rate of change first for this top one. So if we look at the exponent, it's already just t by itself, so we don't have to do any simplifying to get t by itself. Next, I'm going to write the formula that we had up on top here, and you guys have it in your notes. Okay, so now, what we're looking for is the rate, and the rate is, like I mentioned earlier, it's embedded within the parentheses. So our rate is in here in the 1.078. Okay, but remember that it's 1 plus the rate. So this is right now 1 plus the rate. Now we want to make it so it's just the rate. So if you're looking at this, we have 1 plus r. The rate's in there. We want to get rid of this 1, right? It's a positive 1. So that means we got to subtract 1 away from inside the parentheses. If we take that 1 away, we're just left with the rate. So what we're going to do, we're going to take 1.078, right, the number from this parenthesis, and we're going to subtract the 1 away, and that's just going to leave us with the rate. And that'll be 0.078. But now that is just a decimal. And remember that it's asking for the percent rate of change. So 1, 2. 7.8% rate of change. Now we got to determine whether this is a growth or a decay. So it's a growth when we have a positive rate, and it's a decay when we have a negative rate. So if we look at our rate, this was our rate here. It's 0.078. It's a positive 0.078, so we have a growth. So 7.8% growth. Right, because rate is positive. All right, next example. We got f of t equals 1,500 times 0.873 to the 5t power. Okay, so I'm going to look at my exponent, and I notice that my exponent is not t by itself. So we have to simplify it before we start looking for the rate. So what we're going to do, we're going to do just like we did in our prereqs. We're going to have 0.873. We're going to split the 5 and the t, so 5, and then raise it to the t power. Okay, so just like we did in the prereqs there. Okay. Now, the number inside the parentheses can be simplified. We can take our calculators, put 0.873, and raise it to the 5th power, and that gives us 0.5071. So we're just going to use 4 decimal places for now. So I'm going to bring down my f of t. I didn't simplify anything there. Equals 1,500, that stays the same, times. Now that new number is 0.5071. And again, I rounded it to 4 decimal places. Raised to the t power. Okay, so now I have t by itself, so I can go ahead and I can find the rate here. And remember, to find the rate, this is a times 1 plus r to the t power. It's within the parentheses here. So I'm going to take my 0.5071, subtract my 1 away, and that gives me, so 0.5071 subtract 1 gives me 0.4929. Sorry, negative 0.4929. Okay, so this number here is our rate. Okay, it's not our answer. Remember, it wants it in percents. So I know that in order to get percents, I got to switch this decimal 1, 2. So 49.29%. And my rate is negative. So I know that I have a decay. All right, next example. A town has a nasty outbreak of zombie hamsters. The town's population over the year 2000 was 4,000 people. The population t years after the year 2000 can be found using the function f of t equals 4,000 times 0.96 to the t power. So before we go any further, so far what the problem has told us is that this equation here represents the year 2000. Right? It tells us here the year 2000 can be found using the function, that one right there, 4,000 times 0.96 to the t power. So that there is represented by the year 2000. So that said, what is the town's approximate population in 2002, 2005, and 2015? And then later on, what is the decay or growth rate of the town's population? So first thing I'm going to do, I know that this represents the year 2000. So I'm going to rewrite this formula up here. So I know f of t equals 4,000, right? And 4,000 is the starting population, right? It tells us that. That's our A. Times 0.96. Okay, now my t. I got to determine what my t is here. So for the first one I'm going to do the year 2002. And I'll put 2002 up here. E. So now, I know that the formula represents the year 2000. So from 2000 to 2002, I'm going to count how many years passed. So from 2000, 2001, 2002, it's only 2 years. So my exponent here is going to be 2, because only 2 years has passed. So I plug this into my calculator. So 4,000 times 0.96 to the second power gives me 36864. So 36864.4. Okay, so just a quick thing. Anytime we're talking about something that has some kind of life, we can't have half a life. We can't have half a hamster. So we round it up to the next whole number. So instead of 3686, we put 3687. So in 2002, that's our population there, 3687. Now we got to find the population for the year 2005. So in 2005, we have to determine how many years has passed here. So from 2000 to 2005, you count it up, that's going to be 5 years. So our exponent here is now 5. We grab our calculators, plug this in. If my calculator works, see 4,000 times 0.96 to the fifth power gives me 3262. And lastly, we need to do the year 2015. So f of t equals 4,000 times 0.96 to the 15th power. So again, we pull our calculator because 15 years has passed, so we're going to put 15 as the exponent. 4,000 times 0.96 to the 15th power gives us 2169. Okay, so there we have our 3 years for these hamsters. Okay, and we notice from the year 2000 it had 4,000. Year 2002, it's been decaying, right? It's getting smaller. So from 4,000 went down to 3,687. It continues to go down, and then by year 15, it's down to 2,169. So we notice that this is decaying, right? So we know that it's a decay. Now we got to figure out what is the rate of decay. Okay, and the rate of decay goes back to what our formula was, right? This was A times 1 plus R to the T power, right? Remember to look at the exponent. The exponent's already T, so we can go straight directly to looking at the number inside the parentheses. We could take our 0.96, subtract the 1 away, so that leaves us with the rate. That's negative 0.04. So that's our rate there, and since it's negative, we know it's a decay. That just confirms it. And now we get the percent. So it's a 4% decay per year. Right, and there's your rate. Negative 0.04. Okay, our bacteria problem. So number of bacteria, f of t at any time in hours, can be estimated using the function f of t equals 3,000 times 1.24 to the t power. Yep, so before I go any further, I always want to check to see in my equation, is that t by itself? And yes, it is. So I know that this is a times 1 plus r to the t power. Okay, so let's just go ahead and scroll over that first bullet point. What is the initial size of the bacteria colony? So if we're looking for the initial size, that's given to us. We know that A represents initial size, and A is 3,000. So 3,000 is the initial size or the starting size of this bacteria colony. Okay, now bullet 2. Is the bacteria population exponentially decaying or growing? Okay, remember to find whether it's decay or growth, we have to look at the rate. And the rate is right here within that parenthesis. So we take that 1.24, subtract the 1 away, that leaves us with the rate. So that's 0.24. So the rate is positive, so we know it's a growth, and it's a 24% growth. Okay, so we know that it's growing. And then 24%. All right, now we have another bacteria colony, so now I'm down here. Measured against the bacteria mentioned above, and it can be estimated by the function f of t equals 3,000 times 1.1 to the 2t power. So remember step 1, look at my exponent. Is it t by itself? And no, it's not. So we have to apply our power to power rule. And I'm going to do that over here off to the side. So we have 3,000 raised to the 1.10 power raised to the second raised to the t. Okay, so I took this and I split it this way so I can get t by itself. So now I simplify. I can simplify this. That can simplify down. 1.1 to the second power gives me 1.21. So this is 3,000 times 1.21 to the t power. Now, just confirm. Look at your exponent. It's just t by itself. So now we can use our formula to find what the rate is for this one. right? So remember, this is a times 1 plus r to the t power. And again, to find the rate, it's within that parenthesis there. So I'm going to take 1.21, subtract 1, subtract 1 away. That gives me 0.21. Right, so that there is my rate. That's my rate. Right, but now I want my percent, 1, 2, that's 21%. And my rate is also positive here, so it's a 21% growth. Okay, so now that helps us answer this last question on the bottom. Which bacteria is changing faster, and how can you tell? So we can tell by looking at the growth rate. Our first one here had a 24% growth rate, and our second one down here, the second town, had a 21% growth rate. So, of course, the 24% growth rate is larger, which means the bacteria colony on top is growing faster.